You are sitting in a room, surrounded by objects that possess weight, texture, and a definite position in space. You trust the floor to be solid because your senses and the laws of classical mechanics confirm it to be so. You assume that the history of the universe is a linear progression of cause and effect, stretching back to a singular beginning and moving toward a predictable end. This sense of stability is not a product of logic, but of scale. At the level of human biology, reality appears intuitive. However, when we shift our gaze from the immediate to the structural foundations of the cosmos, that intuition fails. We have spent the last century gathering data, measuring the cosmic microwave background, timing the decay of isotopes, and mapping the distribution of galaxies, only to find that the more precise our measurements become, the less the universe resembles a coherent, objective place. The following observations are not theoretical conjectures or science fiction,
are the calculated, measured consequences of our current understanding of physics. They suggest that the reality you perceive is not the fundamental state of existence, but a specific, limited perspective maintained by a series of deep, structural contradictions. We must address the question of why the universe, when measured objectively, seems to actively resist the logic of its own inhabitants. The fine-tuning paradox. You assume that your existence is a natural byproduct of a hospitable universe, a lucky accident on a rocky planet. But when you examine the physical constants that govern the behavior of matter, such as the strength of gravity or the mass of an electron, you find a precision that defies statistical probability. If the expansion rate of the early universe had differed by 1 part in 10 to the power of $60, the cosmos would have either collapsed back into a singularity or dispersed too rapidly for stars to form. You are living in a reality that appears to have been calibrated to a degree that makes the concept of chance mathematically indistinguishable from intent. Yet we find no evidence of a calibrator. Consider the strength of the electromagnetic force compared to the force of gravity. If gravity were only slightly stronger, stars would burn through their fuel in a matter of millions of years rather than billions, leaving no time for complex biological processes to emerge. If it were slightly weaker, the internal pressure of gas clouds would never overcome their own heat, and stars, the engines of all heavy elements, would never ignite. You would exist in a universe of cold, drifting hydrogen, a dark expanse where chemistry itself is forbidden. This precision extends to the very structure of the atom. The strong nuclear force, which binds protons and neutrons together in the nucleus, sits at a value that seems arbitrarily specific. If this force were a mere 2% stronger, hydrogen would not exist. It would have all been fused into helium in the moments following the Big Bang. Without hydrogen, there is no water, no organic molecules, and no long-lived stars. Conversely, if the force were 5% weaker, the nuclei of essential elements like carbon and oxygen would be unstable and fall apart. The carbon in your DNA and the oxygen in your lungs exist only because of a numerical razor's edge that was established before the first second of time had elapsed. We refer to these values as fundamental constants. They are the fixed numbers in the equations of physics that we cannot derive from any deeper theory. We simply measure them. There is no known reason why the mass of a proton is exactly 1,836 times heavier than an electron. There is no logical necessity for the cosmological constant, the energy density of empty space, to be as small as it is. Yet,
If that constant were larger by even a tiny fraction, the acceleration of the universe would have shredded galaxies apart before they could even coalesce. You find yourself in a Goldilocks universe. But the window of habitability is not a broad range, it is a mathematical point. When you calculate the odds of all these constants aligning simultaneously to allow for the existence of matter, you arrive at a number so vanishingly small that it challenges the utility of the word random. In any other context, such a result would be discarded as an impossibility. The observation of this fine-tuning leaves us with a quiet structural unease. We are forced to confront the fact that the universe appears to be a highly specific machine, yet we observe no operator and no blueprint. We are left to wonder if we are the beneficiaries of an infinite series of cosmic lotteries, or if our understanding of the vacuum is missing a fundamental constraint that forces these numbers into place. The data suggests that the universe is not a neutral environment, but a system that has been narrowly defined to permit your perception of it, for reasons the measurements cannot explain. The Great Attractor. You believe the motion of your galaxy is governed by the predictable expansion of spacetime, a uniform outward drift from a central origin. However, mapping the movement of the Milky Way and its neighbors reveals a localized defiance of this expansion. Something massive, hidden behind the zone of avoidance, the dust-shrouded plane of our own galaxy, is exerting a gravitational pull so immense that it is drawing hundreds of thousands of galaxies toward a single point. You are currently being pulled toward an invisible destination at 600 kilometers per second, moving toward a structure whose nature we cannot see and whose influence we cannot escape. This motion is not a subtle drift. It is a systematic, high-velocity migration that contradicts the standard model of a smooth, uniform Hubble flow. While the universe as a whole continues to inflate, our entire local cosmic neighborhood, an area spanning hundreds of millions of light-years known as the Laniakea supercluster, is being rerouted. We are part of a cosmic stream, a flow of matter sliding down a gravitational gradient toward a concentrated anomaly. In the language of astrophysics, this is a peculiar velocity, a term that masks the unsettling reality. We are moving in a way that the general expansion of space cannot explain. The difficulty in identifying this source lies in our own perspective. To look toward the Great Attractor, we must look through the disk of the Milky Way. This region, the zone of avoidance, is choked with thick clouds of interstellar gas and stellar debris that block visible light. We are effectively blind to the very thing that dictates our long-term trajectory. It was only through X-ray and radio astronomy that we began to see through the veil, discovering a massive concentration of mass known as the Norma cluster. Yet even this cluster, with its thousands of galaxies, does not possess enough mass to account for the speed at which we are moving. The Norma cluster is merely a marker on the road towards something even more substantial. Further study has revealed that the Great Attractor itself may be part of an even larger structure. Our local flow appears to be heading toward the Shapley supercluster, a titanic collection of over 8,000 galaxies. This suggests a hierarchy of influence that extends far beyond our local horizon. You are not an inhabitant of a static point in space. You are a passenger on a galactic scale, caught in a current generated by a mass so large it warps the local expansion of the universe. The scale of this movement implies that the distribution of matter in the cosmos is far more lumpy and irregular than our foundational theories suggest. This creates a conflict in our understanding of the universe's evolution. If the Big Bang was a uniform explosion of energy, matter should be distributed with relative equality. Instead, we see these vast superstructures acting as gravitational drains. This raises the question of what happens when we eventually reach the center of this pull. At our current velocity, it would take billions of years to arrive, but the physics of the journey are already clear. We are participating in a grand collapse of local structure, a gathering of matter into increasingly dense hubs of gravity that will eventually dominate their surroundings. The presence of the great attractor reminds us that we are subject to forces we cannot see and did not anticipate. It suggests that our view of the cosmos as a predictable, expanding balloon is an oversimplification. Beneath the surface of that expansion, there are currents and eddies of immense power. You are moving through the dark, toward a destination that has been calling to your galaxy since before the Earth was formed, driven by a gravitational anomaly that we can measure with precision, but cannot yet fully comprehend. The Boltzmann brain. The second law of thermodynamics dictates that entropy must increase, meaning the universe moves from order to chaos. You view your own complex, ordered brain as a product of billions of years of biological evolution. Yet, in a universe of infinite time and fluctuating energy, the statistical probability of a fully formed, conscious brain spontaneously appearing in the vacuum, complete with false memories of a life and a world, is higher than the probability of the entire universe evolving into its current state. You cannot prove that you are a biological entity on a planet. The data suggests it is more likely that you are a momentary fluctuation in a void. This paradox arises from the fundamental nature of probability and the vast timeline of the cosmos. In a system at thermal equilibrium, such as the heat death towards which our universe is arguably headed, there is a non-zero probability that particles will randomly collide and arrange themselves into a structured state. While the odds of air molecules in a room spontaneously gathering in one corner are astronomically low, in an infinite time frame, that event becomes a mathematical certainty. If you wait long enough, the vacuum will eventually cough up an object. The question is not whether the universe can create a brain through random fluctuation, but rather which is more expensive in terms of entropy: a single brain or an entire universe filled with billions of galaxies and trillions of stars. To produce a human brain via the standard cosmological path requires a massive low-entropy event like the Big Bang, followed by 13.8 billion years of precise physical interactions, the formation of specific heavy elements in stellar furnaces, and the complex trial and error of biological evolution. This requires a staggering amount of order. Statistically, it is far cheaper for the universe to simply undergo a localized random fluctuation that assembles a single conscious observer in the dark. This entity, the Boltzmann brain, would exist for only a fraction of a second, but in that moment, its neural pathways would be encoded with the illusion of a past, the sensation of sitting in a chair, and the conviction that it is reading these words. The discomfort lies in the fact that we have no empirical way to distinguish between these two scenarios. Every memory you possess, your childhood, the smell of rain, the laws of physics you've learned, is simply a specific arrangement of atoms in your brain. If those atoms were arranged in that exact configuration by a random fluctuation in the void, you would feel exactly as you do now. You would believe you have a body, a home, and a history. You would perceive a world around you that is internally consistent. But there would be no world. There would only be you, a lonely flicker of consciousness, surrounded by an infinite, chaotic vacuum. If we accept the current models of an eternally expanding universe, the number of Boltzmann brains produced over infinite time will vastly outnumber the number of evolved brains that lived during the brief, habitable era of stars. This leads to a logical crisis. If the majority of observers in the history of the cosmos are momentary fluctuations, then you, as an observer, are statistically more likely to be one of them. The very observations you use to prove the existence of a real, physical universe become suspect, as they could be part of the false dataset pre-programmed into your temporary consciousness. This paradox suggests that our current cosmological models may be missing a vital component, or that the universe is fundamentally different from what we perceive. It implies that the order we see around us is not the norm, but a radical outlier. We are left to grapple with the possibility that the most stable thing in your reality is not the floor beneath your feet or the stars in the sky, but the fleeting, unverified electrical signals occurring within a mind that may have no physical home. The cosmological lithium problem. You rely on Big Bang nucleosynthesis to explain the chemical composition of everything you see. Our models perfectly predict the abundance of hydrogen and helium observed in the oldest stars. However, when we measure lithium-7, the numbers fail. There is 3 times less lithium in the ancient universe than our fundamental laws of physics require there to be. This is not a rounding error. It is a fundamental gap in our understanding of how matter was forged. The elements that make up your world are missing a foundational component of their own history, suggesting our record of the beginning is structurally flawed. This discrepancy is known as the cosmological lithium problem, and it strikes at the heart of our claim to understand the first 3 minutes of time. The physics of nucleosynthesis are governed by the same nuclear reactions we have tested and verified in particle accelerators for decades. When we input the known density of baryons, the matter that makes up atoms, into our equations, the output for hydrogen and its isotope, deuterium, matches our telescopic observations with startling precision. Helium-4 follows suit, but lithium-7 remains a defiant outlier. Every ancient, metal-poor star we observe in the galactic halo should act as a pristine fossil of the early universe. Yet these stars consistently show a plateau of lithium that is significantly lower than what the Big Bang should have produced. To reconcile this, we must look for a mechanism that could have destroyed the missing lithium. One possibility is that it was processed within the first generation of stars, burned away by internal mixing and nuclear fusion. However, the stars we measure are so old and so pure that they lack the convective power to transport surface lithium deep enough into their cores to be destroyed. If the lithium was there at the start, it should still be there now. The fact that it is missing suggests that it was either never created in the quantities we expect, or was removed by a process that is currently absent from our standard model of physics. This opens a door to more unsettling possibilities. Perhaps our understanding of the fundamental constants during the early universe is incomplete. If the strength of the nuclear forces fluctuated even slightly in those first moments, the production of lithium would be the first thing to deviate. Or, more radically, the missing lithium might have been destroyed by the decay of unidentified particles, such as dark matter candidates that interacted with the hot primordial plasma. In this scenario, the very matter you are made of was shaped by a violent, invisible interaction with a substance we still cannot define. The lithium problem is not merely a technical glitch for astronomers to solve. It represents a crack in the foundation of the cosmic narrative. We tell a story of a universe that began in a predictable, mathematically elegant way. Yet, when we look at the actual building blocks of reality, the numbers do not add up. The missing lithium is a silent witness to an event or a physical law that we have yet to discover. It implies that the purity of the early universe is an illusion, and that our origins were influenced by factors that remain entirely hidden from our current instruments. If we cannot account for the basic chemistry of the beginning, we must ask what else we have misinterpreted. We are building our understanding of the cosmos on a chemical ledger that shows a massive, unexplained deficit. This suggests that the universe you see is not the result of a simple linear expansion of known forces, but the product of a more complex and perhaps more chaotic set of conditions that we are only beginning to glimpse. The vacuum catastrophe. You perceive the empty space between atoms as a nullity, a simple background for matter to exist within. Quantum field theory, however, calculates that this vacuum is teeming with zero-point energy. When we use our most successful theories to calculate the energy density of the vacuum, the result is 10,120 times larger than the energy we actually observe through the expansion of the universe. This is the largest discrepancy between theory and observation in the history of science. The space you inhabit should, by all accounts, possess enough energy to explode the universe instantly, yet it remains silent and inert. This conflict arises from the fact that in quantum mechanics, the vacuum is never truly empty. According to the uncertainty principle, energy and time share a relationship that allows for the spontaneous appearance of virtual particles, pairs of matter and antimatter that pop into existence and annihilate one another in an interval too brief to be measured directly. However, the energy associated with these fluctuations is real. It possesses a weight. When physicists attempt to sum up the energy of all these fluctuations across all possible fields, the resulting value is a number so gargantuan that it defies any physical description. It suggests that every cubic centimeter of nothingness contains more energy than all the stars in the observable universe combined. If this calculated energy were present, gravity would react to it. According to general relativity, energy density curves space-time. If the vacuum possessed the energy density suggested by quantum field theory, the universe would have expanded so violently and so rapidly during its first moments that atoms could never have formed. Space would have been ripped apart by its own internal tension. Yet, when we look at the actual expansion rate of the universe, measured through the observation of distant supernovae, we find a value for the cosmological constant that is nearly zero. The discrepancy is not a minor error. It is a factor of a 1 followed by 120 zeros. This is the vacuum catastrophe. It reveals a fundamental schism between our two most successful ways of describing reality. Quantum mechanics, which governs the very small, and general relativity, which governs the very large, are looking at the same empty space and seem two entirely different universes. One sees an ocean of infinite power. The other sees a calm, nearly flat void. The fact that you are here to observe this suggests that some unknown mechanism is cancelling out almost all of the vacuum energy with a precision that is mathematically haunting. To solve this, we would need to find a way to subtract nearly all of that 10,120 energy. In physics, such a process is called fine-tuning. But the degree of cancellation required here is beyond anything else in science. It would be like balancing a needle on its tip, not for a second, but for billions of years, while a hurricane rages around it. We are forced to consider that our understanding of gravity, or perhaps our understanding of the vacuum itself, is missing a foundational element. The implication is that the stability of your world is a mask. You are standing on a floor of explosive potential, held back by a mathematical cancellation we cannot explain. If this balance were to shift by even a fraction of a percent, the fabric of space-time would instantly respond to the true weight of the vacuum. The silence of empty space is not a sign of its passivity. It is a sign of a hidden, perfect equilibrium that allows reality to exist in spite of its own calculations. The black hole information paradox. You accept that the past is fixed and that information, once created, cannot be uncreated. If you burn a book, the information is scrambled but still exists in the arrangement of ash and smoke. But when matter enters a black hole, and that black hole eventually evaporates via Hawking radiation, the information appears to vanish entirely from the fabric of reality. If information can be deleted, then the principle of causality, the idea that the present is determined by the past, is an illusion. Your entire history could be erased without leaving a trace in the physical laws of the cosmos. This conflict arises from a fundamental requirement of quantum mechanics known as unitarity. Unitarity dictates that the sum of all probabilities in a system must always equal 1, which implies that if you have the complete description of a system at any given moment, you should be able to mathematically reconstruct its past and predict its future. Information, the specific arrangement and state of particles, is the currency of this conservation law. In the macroscopic world, entropy makes it difficult to retrieve information, but the laws of physics insist it is never truly destroyed. However, black holes introduce a gravitational intensity that seems to override this quantum mandate. When an object crosses the event horizon, it is removed from the observable universe. According to general relativity, that object is crushed into a singularity. In the 1970s, it was discovered that black holes are not eternally stable. They emit radiation due to quantum effects at the event horizon. This Hawking radiation is thermal and featureless. It carries away mass and energy, but it does not appear to carry away the specific data of what fell in. As the black hole shrinks and eventually vanishes, the information that was once inside has nowhere to go. It is not merely hidden, it is effectively deleted from the timeline of the universe. If information can be lost, the consequences for our understanding of reality are catastrophic. It would mean that the universe does not have a memory. If two different paths can lead to the exact same state, a vacuum filled with uniform thermal radiation, then the link between cause and effect is broken. We would inhabit a universe where the laws of physics are not time-reversible. If the information of a star or a human being can be reduced to nothingness, then the laws we use to describe the cosmos are merely temporary approximations that fail at the most fundamental level. Attempts to resolve this paradox have led to even more unsettling conclusions. One prominent theory, the holographic principle, suggests that information never actually enters the black hole, but is instead encoded on the two-dimensional surface of the event horizon. This would mean that the three-dimensional object that fell in was an illusion, a projection of data stored on a boundary. Another proposal, the firewall hypothesis, suggests that the event horizon is actually a region of intense energy that incinerates anything attempting to cross it, fundamentally altering our understanding of space-time continuity. We are left with a choice between two impossibilities. Either information is destroyed, which invalidates the foundations of quantum mechanics, or our understanding of space-time and locality is a facade. The paradox suggests that at the center of every galaxy lies a phenomenon that is actively dismantling the logic of the universe. It implies that your existence and the history of everything you have ever known exists in a fragile state that the laws of gravity are capable of unmaking without leaving a single photon of evidence behind. The Eridanus supervoid. You expect the distribution of matter in the universe to be roughly isotropic, meaning it looks the same in every direction. But when we look at the cosmic microwave background radiation, we find a cold spot that is significantly larger and emptier than any model allows. It is a region of nothingness spanning nearly 1 billion light-years, where there are far fewer galaxies than there should be. It suggests a massive bruise on the fabric of our universe, leading some to conclude it is the physical imprint of a collision with another universe, an external force acting upon our closed system. Standard cosmology is built upon the cosmological principle, the assumption that, on a large enough scale, the universe is homogeneous. We expect fluctuations in the temperature of the early universe to follow a Gaussian distribution, random, small, and predictable. However, the Wilkinson Microwave Anisotropy Probe, WMAP, and the subsequent Planck satellite mission confirmed a statistical anomaly in the constellation of Eridanus. This is a region where the temperature of the cosmic microwave background is significantly lower than its surroundings. To create such a drop in temperature, light from the early universe must have passed through an area of space so devoid of matter that it lost energy via the integrated Sachs-Wolf effect. When we map the galaxies in this direction, we do not find the typical cosmic web of filaments and nodes. Instead, we find a void. While space is largely empty, the Eridanus supervoid is an outlier of impossible proportions. It spans approximately 1.8 billion light-years. To put this in perspective, it would take merely 2 billion years for light itself to cross this expanse of nothingness. There is no existing model of dark matter or gravitational collapse that can explain how a hole of this magnitude could have formed in the 13.8 billion years since the Big Bang. The universe simply has not existed long enough for gravity to have cleared such a vast volume of space. This lack of internal explanation forces us to look beyond the boundaries of our own observable horizon. If the void cannot be explained by internal physics, it may be the result of an external interaction. Some theoretical models suggest that our universe is just one bubble in a larger inflationary sea, a multiverse where different realities occasionally drift into one another. The Eridanus supervoid could be the scar left behind from a quantum entanglement between our universe and another. In this view, the cold spot is not a void of matter, but a point of contact, a place where the fundamental laws of another reality pressed against ours, displacing matter and energy on a scale we cannot replicate. The presence of the supervoid suggests that our universe is not a closed, self-contained system. It implies that there are weather patterns on a scale larger than the cosmos itself, and that we are susceptible to external forces that do not obey our local laws of physics. If this is a collision site, it means that the vacuum we inhabit is not the only one, and that our entire history has been influenced by a neighbor we can never truly see. You are forced to reconcile the fact that the universe is not the uniform, elegant structure we were promised. It is irregular, scarred, and perhaps even wounded. The Eridanus supervoid stands as a silent monument to the possibility that we are not the masters of our own space, but residents of a bubble that is being buffeted by the vast, unknown pressures of an environment we are fundamentally unequipped to measure. The Fermi paradox. You consider the sheer scale of the observable universe, with its trillions of galaxies and quintillions of habitable planets, and conclude that life must be a common occurrence. The age of the universe provides ample time for civilizations to have colonized entire galaxies, leaving behind detectable signatures of their technology. Yet when we listen to the stars, we find a silence that is total and absolute. The lack of evidence for others suggests either that life is an impossible fluke, or that there is a great filter, a catastrophic event that awaits every civilization, including yours, before it can leave its home. This paradox is not merely a question of missing signals, it is a mathematical contradiction. The Drake equation, which estimates the number of active, communicative extraterrestrial civilizations in the Milky Way, suggests that even with conservative variables, the galaxy should be teeming with life. Given that our sun is relatively young compared to the age of the galaxy, there could be civilizations that are millions, if not billions of years more advanced than our own. At even a fraction of the speed of light, such a civilization could colonize the entire Milky Way in a few million years, a blink of an eye in cosmic time. Yet we see no Dyson spheres, no self-replicating von Neumann probes, and no radio beacons. This leads to the unsettling concept of the Great Filter. This theory suggests that, at some point in the progression from primordial soup to galactic empire, there is a barrier that is almost impossible to cross. If the filter is behind us, in the transition from prokaryotic to eukaryotic cells, or the development of complex intelligence, then we are among the few, or perhaps the only, survivors. But if the filter lies ahead of us, it implies that every civilization reaches a certain level of technological maturity only to be annihilated by a predictable, universal catastrophe. This could be self-destruction via nuclear or biological warfare, or perhaps a technological black hole, such as the creation of an uncontrollable artificial intelligence. The silence of the universe is a data point in itself. It is a measurement of a void where there should be activity. When we look at the stars, we are not just looking at distance, we are looking at time. We see the universe as it was millions of years ago, and still, there is no evidence of large-scale engineering. This suggests that either the conditions for life are so fragile that they are almost never met, or that the lifespan of a technological civilization is so short that they never overlap in time. We may be living in a graveyard of civilizations that were born and died before we even learned to walk upright. There is also the possibility of the dark forest hypothesis. This suggests that the universe is not empty, but occupied by civilizations that have learned the ultimate lesson of survival. Any civilization that reveals its location is a target for more advanced, predatory neighbors. In this scenario, the stars are silent not because no one is there, but because everyone is hiding. Our own radio transmissions, leaking into space for the last century, would not be a message to friends, but a beacon to predators. The Fermi paradox forces you to confront the isolation of your species. Whether we are alone because we are a fluke of biology, or because we haven't yet met the wall that killed everyone else, the implication is the same. Our existence is not part of a crowded, vibrant community of worlds. it is a solitary flare in an immense, darkening room. The data tells us that the universe is indifferent to life, and the absence of others serves as a grim warning that the path we are on has likely been traveled before, ending in a silence we are only now beginning to hear. Quantum entanglement and locality. You believe that for one object to affect another, they must interact or exchange a signal across space. Quantum mechanics observes otherwise. When two particles become entangled, a change to the state of one is reflected in the other instantaneously, regardless of the distance between them. This violates the speed of light as a universal limit for communication. It implies that distance is a secondary construct, and that at a fundamental level, the universe remains a single, undivided point where everything is still in immediate contact with everything else. In your daily life, you rely on the principle of locality, the idea that an object is only influenced by its immediate surroundings. If you wish to move a stone, you must touch it or use a tool that exerts a force upon it. This intuition is backed by special relativity, which establishes the speed of light, c, as the absolute cosmic speed limit. No information, no signal, and no causal influence can travel faster than roughly 300,000 kilometers per second. This limit creates the light cone of your existence, defining what can and cannot affect you. However, at the subatomic level, the universe ignores these boundaries. When two particles, such as electrons or photons, interact in a specific way, they enter a state of entanglement. They cease to have individual identities and instead share a single wave function. If you separate these particles by the width of a room, a galaxy, or the entire observable universe, they remain mathematically linked. If you measure the spin of one particle and find it to be up, the other particle will be found to be down the exact moment it is measured. There is no travel time. There is no signal sent between them. The correlation is 100%, and it is instantaneous. This phenomenon, which Albert Einstein famously dismissed as spooky action at a distance, has been verified in countless Bell test experiments. The results are consistent. The universe is non-local. This suggests that our perception of three-dimensional space is a superficial layer of reality. If two points can interact without crossing the distance between them, then that distance does not exist in the way we think it does. It implies that the separation of objects is a decorative feature of our perspective rather than a fundamental truth of the cosmos. If we follow this logic to its origin, the implications are unsettling. At the moment of the Big Bang, every particle in the universe existed in a state of extreme proximity and interaction. If entanglement persists through expansion, it is theoretically possible that everything in the cosmos remains subtly entangled with everything else. The atoms in your brain may be correlated with particles in the heart of a distant quasar or the cold reaches of the Buddha's void. You are not an isolated observer looking out at a distant world. You are part of a singular, interconnected web where the concept of here and there is a persistent illusion. This dismantling of locality suggests that the universe is not a collection of separate parts, but a unified field where information is shared holistically. We perceive space because our biological senses are tuned to a scale where light speed delays are meaningful. But the measurements of quantum mechanics reveal a reality that is fundamentally indivisible. We are left to wonder if the vast distances of the night sky are merely a trick of the light, hiding the fact that we have never actually moved away from the singular point where it all began. The dark matter ghost. You observe the rotation of galaxies and find that they spin much faster than the visible matter within them should allow. According to the laws of gravity, galaxies should fly apart, yet they stay held together by an invisible, untouchable substance we call dark matter. It makes up 85% of all matter in existence, passing through your body at this very moment without interaction. We cannot see it, feel it, or measure it directly. We only know it is there because the universe behaves as if it is being cradled by a ghost we are not permitted to perceive. This discrepancy was first brought to light by Vera Rubin's observations of galactic rotation curves. In a solar system, the planets furthest from the Sun move the slowest, as gravity weakens with distance. Logic dictates that stars at the outer edges of a galaxy should behave the same way. Instead, measurements show that these peripheral stars move at nearly the same speed as those near the center. The visible mass of the galaxy, the stars, gas, and dust, simply does not provide enough gravitational glue to account for this. Without an immense, unseen source of mass providing additional gravity, every spiral galaxy in the sky should have disintegrated into a spray of lone stars billions of years ago. We have attempted to find this matter across every spectrum of light, from radio waves to gamma rays, and we have found nothing. Dark matter does not emit, absorb, or reflect electromagnetic radiation. It is essentially transparent to the very force we use to define the physical world. This implies that dark matter is not made of atoms, protons, or electrons. It is a form of non-baryonic matter that exists outside the standard model of particle physics. It interacts with the rest of the universe through gravity alone, acting as a structural scaffolding upon which the visible world is built. The scale of this presence is overwhelming. When we look at the cosmic web, the largest known structure in the universe, we are seeing the distribution of dark matter. Visible galaxies are merely the bright froth on the crest of invisible waves. Computer simulations of the early universe show that without the gravitational wells created by dark matter, ordinary matter would have never clumped together densely enough to form stars. You owe your existence to a substance that you can never touch and that refuses to acknowledge your presence. This creates a profound observational crisis. We are forced to admit that 85% of the matter in the universe is dark, while the remaining 15%, everything we have ever seen, touched, or measured, is a minority. We are the anomaly. We live in a world made of light matter, yet we are drifting through a dense ocean of particles that pass through our flesh, our planets, and our suns as if we were mere ghosts ourselves. There are billions of dark matter particles passing through your thumbnail every second, yet they leave no trace, trigger no nerves, and cause no heat. The unsettling implication is that there is an entire shadow infrastructure to the cosmos that remains fundamentally inaccessible to us. We are like residents of a house who can feel the weight of someone walking on the floor above, but can never find the stairs. Our mathematical models are precise enough to tell us exactly how much dark matter exists, yet we are no closer to understanding what it is. It suggests that the reality we perceive is a thin, illuminated surface, and that the true substance of the universe is something alien, silent, and eternally beyond our reach. The arrow of time. You experience time as a river, flowing from the past into the future. You remember yesterday, but not tomorrow. However, the fundamental laws of physics, from Newton's equations to general relativity, are time-symmetric. They work perfectly well whether time flows forward or backward. There is nothing in the math that requires time to move in one direction. Your perception of now is a psychological imposition on a physical reality where all moments in time exist simultaneously, like frames in a film that has already been shot. If you were to film a video of a single planet orbiting a star and play it in reverse, the physics would remain perfectly valid. No law of gravitation or motion would be violated. At the level of individual particles and fundamental forces, there is no forward and no back. The equations are indifferent to the sign of the time variable t. Yet, in the macroscopic world you inhabit, you never see a shattered glass reassemble itself or heat flow from a cold cup of coffee back into the surrounding air. This unidirectional flow is the arrow of time, and its origin is not found in the laws of motion, but in the second law of thermodynamics, entropy. Entropy is a measure of disorder, and the law states that in a closed system, it must always increase. You perceive the transition from low entropy, an ordered state, to high entropy, a disordered state, as the passage of time. This suggests that the arrow is not a property of time itself, but a consequence of the initial conditions of the universe. For the second law to hold true today, the universe must have started in a state of impossibly low entropy. This is the past hypothesis. It implies that all of history is simply the slow, inevitable unwinding of a highly compressed spring that was set at the moment of the Big Bang. This leads to the block universe theory, a consequence of Einstein's special relativity. Relativity teaches us that there is no universal now. Two observers moving at different speeds will disagree on the simultaneity of events. If now is relative, then the past and the future cannot be fundamentally different from the present. Under this model, space-time is a four-dimensional loaf of bread. Your birth, your current breath, and your eventual death are all equally real and permanently etched into the geometry of the cosmos. The distinction you make between the already happened and the yet to come is a biological illusion, a byproduct of how your brain processes the entropic gradient. The implications of this are quietly devastating for the concept of free will. If the future already exists as a fixed coordinate in the block universe, then every choice you believe you are making is merely a segment of a path you are already traveling. You are like a passenger on a train, looking out the window at a landscape that is already there. You feel the motion, and you see the terrain change, but the tracks were laid down long before you boarded. The present is simply the localized spotlight of your consciousness moving through a static, four-dimensional structure. We are left to wonder why our consciousness is trapped in this specific, forward-moving perspective. If the math allows for time to be a two-way street, our inability to perceive it as such is a limitation of our hardware, not a feature of the universe. The data indicates that time does not pass in any physical sense. Instead, we are frozen within a giant, unchanging crystalline structure of events, forever replaying the same moments in a reality where nothing ever truly ends and nothing truly begins. The simulation argument. You trust that your senses provide a direct window into a physical world, but as our computing power increases, we approach the ability to simulate entire universes populated by conscious entities. If such simulations are possible, then statistically, there would be millions of simulated realities for every one base reality.
The mathematical probability that you are living in the original physical universe is nearly zero. Every observation you make, every law of physics you discover, may simply be a parameter of a program designed by an intelligence you can never observe. This logic, formalized by philosopher Nick Bostrom, rests on three possibilities: that civilizations go extinct before reaching the technological maturity to run such simulations, that they reach that maturity that choose not to run them, or that we are almost certainly living in a simulation. Given our own current trajectory, progressing from rudimentary two-dimensional games to immersive virtual realities and complex neural network simulations in less than a century, the second and third options become increasingly plausible. If a civilization ever reaches a post-human stage, where they possess the computing power of a planetary mass, they could simulate the entire history of their ancestors with a negligible expenditure of energy. If such a technology is possible, it would likely be used thousands or millions of times. This creates a nested hierarchy of realities. In this scenario, there is only one base reality, but there are an infinite number of ancestor simulations running within it, and potentially simulations within those simulations. Statistically, if you find yourself as a conscious observer, you must ask, what are the odds that you are the inhabitant of the single, original universe, rather than one of the billions of digital facsimiles? Mathematically, the answer is a rounding error. Your conviction that you are real is a data point that exists within every simulated mind as well. We begin to find unsettling hints of this digital architecture in the very laws of physics we have measured. In computer science, a simulation must have a limit to its resolution to remain computationally efficient. In our universe, we find exactly such a limit: the Planck scale. Below a certain length, concepts of space and time cease to be smooth and instead become quantized, pixelated. Furthermore, the behavior of quantum particles, which exist as mere probability waves until they are observed, mirrors the lazy loading techniques used in modern game engines, where the environment is only rendered when a player looks at it to save processing power. This perspective recontextualizes the fine-tuning of the universe. The precise constants of gravity, electromagnetism, and nuclear forces are no longer mysterious accidents of nature. They are the starting parameters of a simulation. The speed of light is not just a physical constant, but the maximum processing speed of the hardware on which our universe is running. If we ever hit a wall in our understanding of physics, it may not be because our brains are too small, but because we have reached the edge of the program's defined logic. The simulation argument does not require a God in the theological sense, but it does imply a coder, an entity whose motivations and nature are fundamentally unknowable to us. We are participants in an experiment or a recreation, trapped within a system where even our most profound breakthroughs are just discoveries of the software's source code. You are left to wonder if the occasional glitches we see in our data, the anomalies that science cannot explain, are the only times we are seeing the world as it truly is, a flickering projection of a reality we were never meant to inhabit. The false vacuum decay. You assume the universe is in a stable state, having settled into its lowest energy configuration. But there is a possibility that the Higgs field, the field that gives particles mass, is in a metastable or false vacuum. If this is true, a random quantum fluctuation could trigger a bubble of lower energy to form. This bubble would expand at the speed of light, incinerating the universe and rewriting the laws of physics instantly. Because it moves at the speed of light, you would never see it coming. Reality would simply cease to exist before your brain could process the change. To understand this, you must visualize the energy state of the Higgs field as a ball resting on a landscape. In a truly stable universe, the ball sits at the bottom of the deepest possible valley, the true vacuum. However, current measurements of the mass of the Higgs boson and the top quark suggest that our universe may be sitting in a shallow dip, a false vacuum, held back from a deeper valley by a barrier of energy. This is a state of metastability. Like a person standing on a ledge, the system appears stable in the short term, but it possesses a latent potential to fall to a lower, more fundamental level. In the quantum world, things do not always need to go over a barrier to reach a lower energy state. They can tunnel through it. Quantum tunneling is a probabilistic event that can occur at any moment, at any point in space. If a single point in the vacuum were to tunnel into the true vacuum state, it would release a colossal amount of energy, creating an expanding sphere. Within this bubble, the Higgs field would have a different value, which means the fundamental constants of physics would be altered. The very forces that hold your atoms together would change or disappear entirely. The boundary of this bubble is known as a phase transition. As it sweeps through a solar system, it would not be a conventional explosion of fire and pressure. Instead, it would be a fundamental redefinition of matter. Chemistry would become impossible. Protons might decay. Electrons might cease to orbit nuclei. The macro world would be unzipped at the subatomic level. Because the wall of the bubble travels at the speed of light, no information can precede it. There would be no astronomical warning, no flash in the sky, and no time for the nervous system to register a sensation. One moment, the universe is a place of structured complexity. The next, it is a void of different laws. We are currently calculating the half-life of our vacuum, and while the numbers suggest the universe could remain in this false state for 10,000 years, the nature of quantum fluctuations means it could also happen in the next second. It is a cosmic game of Russian roulette, where the trigger is pulled at every point in space, at every moment in time. There is no biological or technological defense against a change in the laws of physics. This measurement forces a re-evaluation of the concept of permanence. We view the laws of nature as eternal truths, the fixed rules of the game. The possibility of false vacuum decay suggests they are merely local, temporary conditions, a weather of the vacuum that has remained calm long enough for us to evolve. We are living in a transient window of physical stability, existing only because the universe has not yet found a way to collapse into its true, final form. The holographic principle. You see yourself as a three-dimensional being inhabiting a three-dimensional space. However, developments in string theory and black hole physics suggest that all the information contained within a volume of space can be described by the information on its boundary. This implies that the universe we experience is a projection, a holographic image, of data stored on a two-dimensional surface at the edge of the cosmos. Your sense of depth and volume is a mathematical illusion, a way for your consciousness to interpret a flat reality. This concept originated not from speculative philosophy, but from a necessity to resolve a crisis in black hole thermodynamics. When an object falls into a black hole, its entropy, the measure of its information content, seems to increase. However, physicists Stephen Hawking and Jacob Bekenstein discovered that the maximum entropy of a black hole is not proportional to its volume, but to its surface area. In our everyday world,
If you want to know how much stuff can fit in a box, you measure the space inside. In the quantum gravity of a black hole, the stuff is limited by the size of the walls. This suggests that the two-dimensional event horizon is the true storage device for everything that has ever entered the abyss. If this rule applies to black holes, it must, by the principle of universality, apply to the universe itself. If the information of a three-dimensional volume can be fully mapped onto a two-dimensional surface without losing any detail, then the third dimension is redundant. It is a mathematical excess that emerges from a deeper, flatter architecture. Think of a credit card hologram, a flat plastic surface that, when struck by light, produces the image of a three-dimensional object with depth and perspective. You are the image. The data that defines your mass, your position, and your history is written in quantum bits on a distant, two-dimensional boundary. This realization fundamentally challenges our understanding of locality. We perceive objects as being near or far because of how they appear in our three-dimensional projection. But if the fundamental data for these objects is stored on a singular boundary at the edge of the observable universe, then every point in your room is technically adjacent to every other point on that surface. The distance between you and a distant star is a convenient interpretation of data points that may be sitting side by side on the cosmic horizon. Our reality is not a place so much as it is a readout of a massive, distant data set. The implications extend to the very nature of matter. If you are a projection, then the solidity you feel is merely the way the code is translated by your senses. We are currently searching for holographic noise, tiny fluctuations in the fabric of space-time that would act like the pixels on a screen. If the resolution of the universe is finite, it means there is a limit to how much information space can hold. If we zoom in far enough, the smooth geometry of your world should break down into a jittery, two-dimensional static. We find ourselves in a reality that is essentially hollow. We are the inhabitants of the bulk, unaware that the laws of physics we study are merely the shadows cast by a more fundamental set of interactions occurring on a surface we can never reach. The data suggests that your life is not a journey through a vast, three-dimensional void, but a complex flicker of information on a boundary, a story told in two dimensions that has convinced itself it has depth. The Kugelblitz. You understand that matter creates gravity, and enough matter in one place creates a black hole. But Einstein's equations show that energy and mass are equivalent. If you were to concentrate enough light or radiation into a small enough space, the energy itself would collapse into a black hole, a Kugelblitz. This would be a region of space made of pure light that is so intense it becomes a trap from which not even light can escape. It is a paradox of illumination, creating absolute darkness, where the very tool we use to see reality becomes the mechanism that hides it. The term, German for ball lightning, describes a phenomenon that exists at the extreme intersection of general relativity and thermodynamics. In standard stellar evolution, a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own weight. This is matter-driven gravity. However, the E equals mc squared relation dictates that energy, whether in the form of heat, kinetic motion, or photons, contributes to the curvature of spacetime just as surely as atoms do. If you were to focus a sufficiently powerful array of lasers into a microscopic volume, the energy density would eventually reach a critical threshold known as the Schwarzschild radius. At this moment, the photons would no longer pass through each other. Their collective gravitational pull would become so great that they would warp space-time into a closed loop. Once a Kugelblitz forms, it is indistinguishable from a black hole made of matter. It possesses mass, charge, and spin. It develops an event horizon, a point of no return. The irony is total. The very photons that were meant to illuminate the void are now the architects of a prison from which no signal can ever be sent. The light has, in a literal sense, become too heavy to exist. This demonstrates that gravity is not a property exclusive to stuff or objects, but a consequence of energy density itself. Even the most ethereal and massless entities in the universe, if gathered in sufficient quantity, can create a hole in the fabric of reality. The existence of a Kugelblitz would represent a terrifying form of power. Unlike a traditional black hole, which requires the death of a sun, a Kugelblitz could theoretically be engineered by a sufficiently advanced civilization. It would be a concentrated battery of pure radiation, radiating Hawking temperature inversely, proportional to its mass. A small Kugelblitz would be incredibly hot and would evaporate rapidly, releasing a gargantuan burst of gamma radiation. It would be a localized, artificial sun that eventually consumes itself in a flash of blinding light, returning the energy to the universe as it dissolves. However, the Kugelblitz also reveals a limit to our own perception. Light is the medium through which we observe and verify the universe. We rely on the speed of light as a constant and its propagation as a guarantee of visibility. The fact that light can clump and hide itself suggests that there are thresholds where the observer's tools fail by their own strength. It implies that if the early universe was sufficiently hot and filled with enough high-energy radiation, microscopic Kugelblitzes could have formed spontaneously, acting as primordial black holes that we have yet to detect. We are left to contemplate the fragility of our sensory world. We exist in a low-energy environment where light moves in straight lines and reveals the shapes of things. But at higher densities, the very medium of sight becomes a blindfold. The Kugelblitz is a reminder that the universe has a maximum capacity for energy. And once that limit is reached, reality stops being a transparent stage and starts collapsing into a series of impenetrable, dark spheres. The strangelet scenario. You are composed of up and down quarks, the stable building blocks of ordinary matter. Deep within the cores of neutron stars, however, the pressure may be high enough to create strange matter, a substance made of strange quarks that is perfectly stable and denser than anything we know. If a single strangelet were to escape and come into contact with ordinary matter, it would convert that matter into strange matter instantly, triggering a chain reaction. If this process began, the entire Earth would be converted into a clump of strange matter the size of a city block in a matter of seconds. This terrifying possibility arises from the strange matter hypothesis, which suggests that strange matter might be the true ground state of all matter. In our everyday experience, the nucleus of an atom is composed of protons and neutrons, which are in turn made of up and down quarks. This configuration is stable at the temperatures and pressures of Earth. However, at extreme densities, such as those found in the heart of a collapsed star, the quarks are squeezed so tightly that they may transition into a new, lower energy state containing strange quarks. Because nature always seeks the lowest energy state, strange matter would be more stable than the atoms that make up your body, your home, and the air you breathe. The danger lies in the infectious nature of this stability. If a small fragment of this substance, a strangelet, were to collide with ordinary matter, it would find itself in contact with a higher energy state. Just as a spark triggers a forest fire by allowing stored energy to be released, the strangelet would catalyze the conversion of nearby nuclei. Protons and neutrons would be unzipped and rearranged into strange matter, releasing energy and more strangelets in the process. It is a subatomic contagion that does not require heat or radiation to spread. It only requires contact. Because strange matter is incredibly dense, the resulting strange Earth would not retain its shape or volume. Gravity would pull the newly converted matter into a tight, ultra-dense sphere. If the Earth were to be infected, the transition would move through the crust, mantle, and core at a speed determined by the rate of nuclear interaction. Within a minute, the planet would collapse. The 7 billion people, the oceans, and the atmosphere would all be compressed into a hyperdense, hot lump of strange matter, no larger than a few hundred meters across. There would be no explosion, only a silent, catastrophic shrinking of reality to a strange matter sphere of equivalent mass. We must ask how such a particle could ever reach us. Supernova explosions, or collisions between neutron stars, could potentially eject strangelets into the interstellar medium, where they would drift through the galaxy like microscopic, invisible mines. While we have never detected a strangelet on Earth, our high-energy particle accelerators, designed to recreate the conditions of the early universe, operate at energy levels that could theoretically produce them. Physicists have calculated the risk and concluded it is negligible, yet the math remains. If our understanding of the quark ground state is even slightly off, we are currently living in a universe where the only thing preventing total structural collapse is the statistical rarity of a single encounter. The strangelet scenario suggests that the matter you perceive as solid and permanent is actually a metastable exception. We are like a film of water caught on a freezing window, existing only because we have not yet touched a crystal of ice. The universe may have already decided that strange matter is its preferred form, and we are simply the last pockets of a complex, fragile arrangement of atoms that has not yet been corrected by the fundamental laws of thermodynamics. The Bootes Void. You are accustomed to a night sky filled with stars and the universe populated by vast clusters of galaxies. But in the direction of the constellation Bootes, there is a spherical region of space 330 million light-years in diameter that is almost entirely empty. According to standard models of galaxy formation, there should be thousands of galaxies in this space. We have found fewer than 100. It is a desert in the middle of an ocean, a great nothing that suggests either our theories of how the universe grew are wrong, or something has actively cleared that region of its contents. To understand the scale of this anomaly, you must consider the density of the average cosmos. Space is mostly empty, but it is structured. Galaxies typically follow a cosmic web of dark matter filaments, like dew on a spider's web. Even the most desolate regions usually contain a predictable scattering of matter. If the Milky Way were at the center of the Bootes Void, we would not have discovered another galaxy until the 1960s. The night sky would be almost entirely black, a terrifyingly empty shroud that would have fundamentally altered the development of human astronomy and philosophy. The existence of such a massive vacancy challenges the lambda-CDM model, our standard framework for the universe. This model assumes that the universe began with tiny quantum fluctuations, that gravity eventually magnified into the filaments and voids we see today. However, there is a physical limit to how large a void can grow within the current age of the universe. Gravity moves at the speed of light. It takes time to pull matter out of one region and deposit it into another. A void 330 million light-years across is simply too large to have formed naturally through gravitational drift alone in only 13.8 billion years. It is a mathematical impossibility that exists as a physical fact. Some researchers have proposed that the Boltzmann void is the result of multiple smaller voids merging together, like soap bubbles joining in a sink. But even this merger hypothesis struggles to explain the sheer absence of dwarf galaxies, the small, dim clusters that should be left behind in the wake of such a process. The void is not just empty of giants. It is scrubbed clean of the debris of cosmic evolution. This leads to more unsettling, non-naturalistic interpretations. If the universe didn't create this hole, we are forced to ask if something else did. One speculative but logically consistent theory involves the expansion of a Type 3 civilization. If an advanced species began to harvest the energy of entire galaxies, they might enclose them in Dyson spheres, effectively turning off the lights of an entire sector of space. Under this interpretation, the Boltzmann void is not empty, but occupied, a region where the stars have been harvested and hidden behind shells of matter to capture every photon of available energy. The Great Nothing would then be the footprint of an intelligence operating on a scale that renders our own planetary concerns invisible. The Boltzmann void remains a silent, observational crisis. It is a place where our laws of physics suggest there should be life, light, and motion, yet we find only a profound and unnatural stillness. Whether it is a flaw in our understanding of gravity or the shadow of a cosmic-scale engineering project, the void serves as a reminder that the universe is capable of producing structures, or lack thereof, that defy the very logic we use to measure them. The CMB Axis of Evil. You believe that the universe has no preferred direction, and that the afterglow of the Big Bang, the cosmic microwave background, should be randomly distributed. Yet when we analyze the temperature fluctuations of the CMB, we find they are aligned with the plane of our own solar system and the direction of our orbit. This axis of evil suggests that the largest structures in the universe are somehow tied to the tiny, insignificant movement of our Earth. It implies either a massive fluke of observation or that we are at a central, privileged position in the cosmos that modern science says we should not occupy. Since the time of Copernicus, the bedrock of astronomy has been the principle of mediocrity, the idea that Earth is not special, not central, and not a focal point for the laws of physics. We assume the universe is isotropic, meaning it looks the same in every direction when viewed on a large enough scale. The cosmic microwave background, CMB, is the ultimate evidence for this, a snapshot of the universe when it was only 380,000 years old. It is the wallpaper of the sky, representing the largest possible scale we can measure. However, data from the WMAP and Planck satellites has revealed a pattern that should not exist if the universe is truly random. When physicists decompose the CMB map into multipoles, mathematical ways of looking at the frequency of temperature variations, they find that the largest features, the quadrupole and octopole, are curiously aligned. More disturbingly, this alignment points directly along the ecliptic, the plane of our solar system's orbit around the Sun. It also correlates with the equinoxes. This is mathematically equivalent to finding that the architecture of a cathedral was designed to align perfectly with a single grain of sand on the floor.
there is no known physical mechanism that should link the cooling of the early universe to the orbital mechanics of a small planet 4 billion years in the future. This leaves us with 3 uncomfortable possibilities. The first is that the data is contaminated. Dust within our own galaxy, or the way our instruments process light, has created a local filter that we are misinterpreting as a cosmic signal. However, after decades of rigorous cleaning and multiple satellite missions, the signal persists. The second possibility is that this is a statistical fluke. In an infinite universe, even the most improbable alignments must happen somewhere. We may simply be the observers who happen to live in the one spot where the background of the universe accidentally mimics the path of our home. The third possibility is the most disturbing, that the cosmological principle is wrong. If the alignment is real and not a fluke, it suggests that the universe has a preferred direction, a top and a bottom, or a left and a right. It would imply that the universe is not the uniform, indifferent expanse we imagined, but is instead structured in a way that relates specifically to our localized frame of reference. This would mean that our current mathematical models of the Big Bang, which rely on the assumption of uniformity, are fundamentally incomplete. The Axis of Evil challenges the very foundation of how we place ourselves in reality. We have spent centuries convincing ourselves that we are a peripheral accident in a vast, uncaring void. To find that the largest structures in existence are oriented toward our tiny ecliptic suggests a level of connection, or a level of error, that science is currently unable to resolve. It suggests that the background of reality is not a neutral stage, but is instead intimately and inexplicably tied to the foreground of our own existence. The heat death of the universe. You view the future as a space for potential and growth, but the second law of thermodynamics is absolute. As the universe expands, matter drifts further apart and energy becomes evenly distributed. Eventually, every star will burn out, every black hole will evaporate, and the temperature of the universe will reach absolute zero. This is not a state of coldness, but a state of nothingness, where no work can be performed and no information can exist. The end of the universe is not a bang, but a permanent, silent equilibrium, where time itself becomes meaningless. This process is driven by the inexorable rise of entropy. In physics, entropy is the measure of molecular disorder or randomness within a system. Every time energy is converted from one form to another, when a star fuses hydrogen or when you move your arm, a portion of that energy is lost as waste heat. This heat is not recoverable. It is energy that can no longer be used to do work. Because the universe is a closed system, the total amount of usable energy is finite and constantly diminishing. We are living in the stelliferous era, a brief, bright flicker in the cosmic timeline where energy gradients are steep enough to support stars, planets, and life. As the expansion of space continues to accelerate, galaxies will be pushed beyond each other's cosmic horizons, leaving the Milky Way and whatever remains of our local group as an isolated island in an infinite dark sea. One by one, the stars will exhaust their nuclear fuel. The small, dim red dwarfs will be the last to flicker out, leaving behind cold cinders of degenerate matter. The universe will enter the degenerate era, populated only by white dwarfs, neutron stars, and black holes. There will be no new light, only the slow, agonizing cooling of dead remnants as they drift toward the absolute zero
of the vacuum. Even these remnants are not permanent. Over vast timescales, matter itself may be unstable. If protons decay, as many grand unified theories predict, the very atoms that make up the cold corpses of stars will dissolve into radiation. The universe will then be dominated by black holes, which will reign for googolls of years. But even these titans are subject to the laws of thermodynamics. Through the slow leak of Hawking radiation, black holes will lose mass until they vanish in a final microscopic pop of gamma rays. What remains is the dark era. The universe will consist only of a thin, cooling soup of photons, neutrinos, and electrons, spread so thin that they rarely, if ever, interact. At this point, the universe has reached its maximum entropy. The temperature is uniform. Because there are no energy differences, no hot stars and cold voids, no physical processes can occur. There is no metabolism, no computation, and no change. This state is the heat death. But the term is a misnomer. It is actually the death of heat. Without change, the concept of time loses its physical meaning. Time is measured by the interval between events, and in a state of perfect equilibrium, no events occur. The universe becomes a static, eternal tomb. Every thought ever conceived, every empire built, and every star that ever shone will have their information erased by the smoothing effect of entropy. You are witnessing the youth of a cosmos that is destined to spend the overwhelming majority of its existence as a cold, featureless, and silent void, where the very notion of happening has ceased to exist. The observer effect. You believe that the world exists independently of whether you are looking at it. But in the double-slit experiment, the act of observing a particle changes its behavior, forcing it to choose a single path instead of existing as a wave of probability. This suggests that reality does not solidify until it is measured. If the universe requires an observer to manifest into a definite state, then the cosmos remained a ghost-like blur of possibilities for billions of years before the first conscious mind evolved to look at it. This fundamental challenge to our sense of objectivity begins at the quantum level. When we do not look at a subatomic particle, such as an electron, it does not occupy a single point in space. Instead, it exists as a wave of probability, a mathematical haze of potential locations, described by the Schrödinger equation. It is simultaneously in multiple places at once. However, the moment we place a detector to see which path the electron takes, the wave function collapses. The haze vanishes, and the particle appears at a single, definite coordinate. The act of gathering information is not a passive observation. It is a creative act that forces the universe to make a decision. This phenomenon, known as the Copenhagen interpretation, implies that the physical properties of the universe are not fixed until they interact with a measuring device or an observer. This raises a profound and disturbing question. What constitutes an observer? In the laboratory, an observer might be a silicon sensor or a human eye, but on a cosmic scale, the implications are far more vast. If measurement is required to bridge the gap between probability and reality, then for the first several billion years of its existence, the universe may have lacked a definite history. It existed as a superposition of all possible states, a trillion different versions of the cosmos overlapping in a silent,
unobserved void.
This leads us to the participatory universe hypothesis, proposed by physicist John Wheeler. He suggested that the universe is a self-observing system. Through us, the universe looks back at its own beginnings, and by doing so, it retroactively solidifies the very Big Bang that led to our creation. This is the delayed choice experiment writ large. In a lab, we can show that a measurement made in the present can determine the path a photon took in the past. If this principle holds true across billions of years, then your act of looking at a distant star does more than just record its light. It may be the final step in ensuring that star existed in a specific way in the first place. The discomfort of the observer effect lies in its removal of a real world existing outside of consciousness. We prefer to think of the universe as a sturdy stage upon which we briefly play our parts. But the data suggests the stage is not built until we step onto it. This creates a logical loop. We cannot exist without a stable universe, but the universe may not be stable without an observer to measure it. The measurements of quantum mechanics do not permit a reality that is independent of the process of measurement. You are left with the realization that your perception is not a window into an objective landscape, but a necessary component of the landscape's existence. The solidity of the chair you sit in, the fixed orbit of the moon, and the certainty of the past are all products of a continuous, ongoing collapse of probability. Without the observer, the universe reverts to a state of mathematical ghostliness, a vast, shimmering field of things that might happen, but never quite do. The neutrino ghost. You think of your body as a solid, impenetrable object. In reality, trillions of neutrinos, nearly massless particles born in the hearts of stars, are streaming through you every second at near light speeds. They pass through the entire Earth as if it were not there. We only detect them with massive underground tanks of pure water, where they occasionally strike an atom and emit a faint blue light. You are a ghost to them, and they are ghosts to you, occupying the same space but existing in entirely different versions of reality. The sheer abundance of these particles is staggering. Every second, about 65 billion neutrinos pass through every square centimeter of your body that faces the sun. They are the screams of nuclear fusion, the byproduct of the intense pressure and temperature within the solar core. Yet, because they lack an electric charge and possess almost no mass, they do not interact via the electromagnetic force. This means they do not touch the atoms in your body. They don't bounce off your skin or get absorbed by your bones. To a neutrino, the vast solid mass of the Earth is merely a slightly hazy patch of vacuum. This lack of interaction makes them the most elusive subjects in the history of physics. To catch them, we have to build observatories that look nothing like telescopes. Facilities like Super Kamiokande in Japan or IceCube in Antarctica use thousands of tons of ultra-pure water or ice buried deep underground to shield out other cosmic interference. When a rare, lucky neutrino happens to collide head-on with an atomic nucleus in the water, it produces a secondary particle that moves faster than the speed of light in that medium. This creates a photonic sonic boom known as Cherenkov radiation, a ghostly blue flash that is the only evidence of the neutrino's passage. But the mystery of the neutrino goes deeper than its transparency. Neutrinos are chameleons of the subatomic world. They come in three distinct types or flavors: electron, muon, and tau. As they travel through space at nearly 300,000 kilometers per second, they constantly oscillate between these flavors. A neutrino that leaves the Sun as an electron neutrino might arrive at Earth as a muon neutrino. This oscillation was the first proof that neutrinos must have mass, however minuscule, because, according to Einstein's special relativity, a truly massless particle moving at exactly c would experience no time and therefore could not change. This discovery suggests that our standard model of particle physics is incomplete. Neutrinos possess a mass that is at least 1,000,000 times smaller than that of an electron, yet we don't know why. Some theories suggest they might be their own antiparticles, Majorana fermions, which would mean they could annihilate themselves under the right conditions. If true, neutrinos might hold the key to why the universe is made of matter at all, rather than an equal mix of matter and antimatter that should have vanished in the first moments after the Big Bang. The ghostly nature of the neutrino forces you to accept that your sensory experience of reality is extremely filtered. You feel the wind and the warmth of the sun, but you are completely blind to the most pervasive matter in the cosmos. You are currently being bathed in the debris of the beginning of time and the death of distant stars, yet your nervous system is tuned to a frequency that misses 99.9% of the action. You exist in a crowded room, surrounded by a cosmic wind of information and history, while perceiving only the silent, empty stillness of the air around you. 22. The past hypothesis. The past hypothesis. You assume the universe started in a state of low entropy, extreme order, because that is what we observe in the CMB. But there is no law in physics that explains why the beginning had to be orderly. Statistically, it is infinitely more likely that the Big Bang should have produced a high-entropy, chaotic mess. The fact that the universe began in a highly specific, low-entropy state is a low-probability event that makes the entire history of the cosmos a statistical impossibility. We are living in the aftermath of a miracle we cannot explain. Entropy is the measure of a system's disorder. In our daily lives, we witness the second law of thermodynamics in constant action. Order naturally devolves into chaos. A glass breaks, but never spontaneously reassembles. A cloud of smoke disperses, but never draws itself back into a cigarette. For these processes to occur in the direction we call forward in time, the starting point must have been more ordered than the ending point. This logic leads us back, step by step, to the very first moment of the universe. For the second law to hold true, the 13.8 billion years, the Big Bang must have been the most ordered, lowest entropy state imaginable. Physicist Roger Penrose calculated the odds of this specific, low-entropy starting condition occurring by sheer chance. To account for the smooth distribution of matter and the precise gravitational configuration of the early universe, the aim of the Big Bang had to be accurate to 1 part in 10 to the power of 123. This is a number so vast that it is impossible to write down. There are not enough atoms in the observable universe to act as digits. If you were to randomly assemble a universe from its constituent parts, you would almost certainly create a giant black hole or a uniform sea of thermal radiation, a state where entropy is already at its maximum and nothing interesting can ever happen. This creates a foundational problem for our understanding of time. Most laws of physics are time-symmetric, meaning they work just as well backward as they do forward. The only reason we perceive an arrow of time is because we are sliding down an entropy gradient. If the Big Bang had started in a high entropy state, there would be no arrow. There would be no past, no future, and no biological processes.
We exist only because the universe began in a state of extreme unlikelihood. We are riding the wake of a cosmic winding up that happened at the dawn of time. And we have no physical theory that explains why the clock was wound in the first place. Some suggest that we live in a multiverse, where an infinite number of big bangs occur with random entropy levels. In this view, we simply happen to be in one of the few universes that started with low entropy, because life cannot evolve in the high entropy messes that constitute the majority of realities. Others propose the Boltzmann brain paradox. If the universe is just a random fluctuation of entropy, it is statistically more likely for a single conscious brain to spontaneously assemble out of the chaos than for an entire trillion galaxy universe to form in a low entropy state. The fact that you see a coherent world around you, rather than a fleeting hallucination in the void, is itself a violation of statistical probability. The past hypothesis forces us to admit that our scientific narrative begins with a massive, unexplained assumption. We can describe everything that happened after the first picosecond of the Big Bang, but we cannot explain why the starting conditions were so exquisitely tuned for order. We are the beneficiaries of an initial state of perfection that defies every law of probability we know. The universe is not a random occurrence. It is a highly specific, highly ordered anomaly, and our entire history is the slow, beautiful decay of that initial, impossible spark. The dark flow. You are told that the universe is expanding uniformly in all directions, but observations of galaxy clusters show them drifting toward a specific patch of sky between the constellations of Centaurus and Vela. This motion is not caused by anything within the observable universe. It suggests that something outside our cosmic horizon, beyond the 46 billion light-years we can see, is exerting a gravitational pull on our entire reality. We are being tugged by a presence that exists outside the limits of our light and our logic. This phenomenon, termed dark flow, was first identified by analyzing the cosmic microwave background, CMB, using the kinematic Sunyaev-Zeldovich effect. By observing how photons from the early universe scatter off the hot gas within massive galaxy clusters, researchers noticed a surprising consistency. Instead of moving randomly as a result of local gravitational interactions, these clusters, some of the largest structures in existence, appear to be part of a vast, coherent stream. They are racing at speeds of approximately 600 to 1,000 kilometers per second toward a singular point on the cosmic horizon. This is not the standard expansion of space. It is a bulk flow, a coordinated migration across the void. The problem is that there is nothing in the observable universe large enough to cause this. Gravity is a localized force. It weakens with distance. To pull hundreds of millions of galaxies in a uniform direction, a mass would need to be so gargantuan that it would dominate our entire sky. Yet, when we look toward Centaurus and Vela, we see nothing that fits the description. This implies that the source of the pull lies beyond the particle horizon, the boundary of the observable universe defined by the distance light has traveled since the Big Bang. We are effectively watching the tail of a dog being wagged by a body that is hidden behind an impenetrable wall of light. This discovery challenges the fundamental cosmological principle, which posits that the universe is homogeneous and isotropic on a large scale. If dark flow is real, it means the universe is lopsided. It suggests that the Great Attractor, a previously identified gravitational anomaly in our local supercluster, is merely a small eddy in a much larger current.
If the matter in our observable bubble is being influenced by something outside of it, then our universe is not a closed system. We are a small province in a much larger, uneven landscape, subject to the gravitational whims of a megaverse that we can
never photograph or visit. The implications for the early universe are even more radical. Some theorists suggest the dark flow is a relic of the period before inflation. In the first fraction of a second after the Big Bang, our region of space might have been entangled with, or adjacent to, a massive concentration of matter. As inflation expanded our pocket of the universe at speeds faster than light, that matter was pushed beyond our horizon, but its gravitational fingerprint remained. We are experiencing the lingering ghost of a pre-cosmic neighbor, a tug from a reality that was separated from ours at the moment of creation. We are left with the unsettling image of our entire observable reality as a small raft caught in a silent, massive current. We look out at our 93 billion light-year sphere and call it everything. But the dark flow tells us we are merely a fragment of a larger whole. We are being drawn toward a destination we can never see, by a force we can never measure, existing in a universe that is being slowly tilted by a weight that sits outside the edge of the world. The antimatter asymmetry. You exist because matter won a war at the dawn of time. For every billion particles of antimatter created in the Big Bang, there were 1,000,000,001 particles of matter. The billion pairs annihilated each other, leaving behind the tiny residue that forms everything you see. Physics tells us that matter and antimatter should have been created in perfectly equal amounts, which would have resulted in a universe made of nothing but pure light. We do not know why the symmetry was broken, or why you are here to ask the question. Our existence is a statistical error that defies the most fundamental symmetries of nature. According to the standard model of particle physics, energy transforms into matter in a process called pair production. When a high-energy photon converts into mass, it always produces a twin, one particle of matter and one particle antimatter. These two are identical in mass, but opposite in charge. If they touch, they instantly annihilate, returning to the state of pure energy from which they came. In the searing heat of the early universe, this creation and destruction happened billions of times a second. By all mathematical accounts, the ledger should have remained balanced. The universe should have been a null-sum game, ending in a featureless void of radiation. Yet, as the universe cooled and the great annihilation concluded, a leftover scrap of matter remained. This tiny excess, roughly one extra particle of matter for every billion matter-antimatter pairs, is the source of every star, planet, and person in the cosmos. This is the baryon asymmetry problem. If the symmetry had been perfect, the stars would never have ignited, and the galaxies would never have formed. The very fact that you can touch your own hand is proof that the laws of physics failed to be fair in the first few microseconds of time. To explain this miracle, physicists look to CP violation, the idea that certain particles behave slightly differently when their charge and spatial coordinates are inverted. If matter and antimatter don't follow the exact same rules, it might explain why one outlasted the other. However, the amount of CP violation we have measured in laboratory experiments with kaons and B mesons is nowhere near enough to account for the vast amount of matter we see.
there is a massive gap between the broken symmetry we can explain and the broken symmetry required for us to exist. This leads to even more radical theories. Some suggest that the missing antimatter isn't actually missing, but was pushed into distant, isolated pockets of the universe during inflation. If this were true, there could be anti-galaxies and anti-stars lurking in the deep voids of space. If an antimatter galaxy were to collide with a matter galaxy, the resulting explosion would be the most violent event in the history of the cosmos, releasing energy on a scale that dwarfs a supernova. However, we see no gamma-ray signatures of such collisions at the edges of our observable horizon, suggesting that the asymmetry is universal. We are left with the realization that the universe is fundamentally biased. The neutral, symmetrical beauty we expect from mathematical laws was discarded at the moment of creation in favor of a messy, physical reality. You are the product of a cosmic glitch, a tiny, unexplained imbalance that prevented the universe from canceling itself out. We live in a world made of the survivors of a prehistoric massacre, and the reason for our victory remains one of the deepest and most haunting secrets of the vacuum. The eternal inflation. You think of the Big Bang as a single, unique event that created everything. But the theory of inflation suggests that the rapid expansion of the early universe never truly stopped. Instead, it only stopped in small pockets, one of which is our universe. Outside our bubble, space is still expanding at exponential speeds, constantly spawning an infinite number of other universes with different laws of physics. In this multiverse, everything that can happen does happen, an infinite number of times. Your life is not a unique story, but a single variation in a never-ending cycle of repetition. To understand this, we must look at the mechanism of inflation itself. In the first trillionth of a second after the Big Bang, the universe underwent a growth spurt so violent that it expanded from the size of a proton to the size of a galaxy. This expansion was driven by an inflaton field, a state of high-energy vacuum. While this field decayed in our region, turning that energy into the matter and radiation we see today, quantum mechanics dictates that the field doesn't decay everywhere at once. In the vast majority of space, the inflation continues forever, moving faster than the speed of light. Forever. Separating these bubble universes from one another. This creates a cosmic landscape that is fundamentally beyond our reach. Because the space between these bubbles is expanding exponentially, no signal, no light, and no traveler can ever cross the gap from our universe to another. We are trapped in a localized pocket of stability, unaware that the void outside our horizon is actually a boiling sea of creation. In this eternal sea, the laws of physics are not universal. They are local bylaws. One bubble might have 10 dimensions. Another might have a version of gravity that repels rather than attracts. The constants of nature we hold dear, the mass of an electron, the strength of the nuclear force, are merely the random result of how the field cooled in our specific corner of the multiverse. The philosophical weight of eternal inflation lies in the concept of infinity. If the inflationary process is truly eternal, it produces an infinite number of pocket universes. In an infinite system, every possible arrangement of matter must occur, and it must occur an infinite number of times.
Somewhere in that sea of bubbles, there is a version of Earth where the dinosaurs were never extinguished. Somewhere, there is a version of you who made the opposite choice in every major life decision. The uniqueness we feel is a result of our limited perspective. In the grander architecture, we are merely one of an infinite number of identical copies. This also offers a controversial solution to the fine-tuning problem. Why is our universe so perfectly suited for life? In an eternal inflation model, the answer is simple. We live here because this is one of the few bubbles where the laws of physics allowed atoms to form. We aren't a miracle. We are a statistical inevitability. For every universe that supports life, there are trillions of sterile, chaotic, or short-lived bubbles that collapsed moments after their birth. We are the beneficiaries of a cosmic lottery that has been running for an eternity. We are left to grapple with the idea that our entire universe is nothing more than a single microscopic pore on the skin of a much larger, restless organism. The Big Bang was not the beginning of time and space, but rather the moment our specific bubble stopped inflating and started aging. We exist in a quiet eddy of a waterfall that never ends, a small, cooling ember in a forest fire of creation that will continue to burn long after our stars have faded and our universe has returned to the void.